You're so brave and strong, walking through the jungle, a rifle in your hand.
Okay, so now let's, now that we've done some things with the directional derivative and the gradient, what we're going to do is go back and actually talk about some properties of both the gradient and the directional derivative. So let's write that down here. So we're going to have the properties of mainly the gradient, but it also involves the directional derivative. So I'll write that too. So of the gradient and directional derivative. I'll just abbreviate here. Okay, so what we're going to start with is that let's go back to the equation that we have the directional derivative in the direction of u of f at some point p. That's equal to the gradient of f at p dotted with our unit vector u. Okay? So what's important to note here is that we have a dot product going on. So let's kind of go back and recall what are the properties of the dot product. So this thing on the right here, so this gradient of f at p dotted with u is equal to the magnitude of the gradient, right, times the magnitude of u times cosine theta, where theta is the angle between the two vectors. So that would be between the gradient at p and the u. Okay, so that's the angle between gradient and u. And then here we see that we have the magnitude of u, and that's a unit vector automatically, so that should be a 1. So what we get is that this is this dot product here, that the directional derivative, right, because this is equal to this is equal to that, is equal to the magnitude of our gradient times cosine of the angle between the gradient and our direction vector, or our unit vector, right? So what we see is, in a more analytical perspective, is that the rate of change of the function, our directional derivative, right, it varies with the cosine of the angle, okay? So what that means, and I'll just write that direction vector thing down here again so we can see it more closely, right? So this is the relation that we have obtained, right? So anyways, so the rate of change, right, the slope of the tangent line, so the rate of change of the function varies. It depends on the cosine of the angle, okay, so this, between the gradient and the direction vector, right? So if we analyze it a little bit more, what we'll see, so I'll write this on the next slide. So we have that the direction vector of f at p is equal to the magnitude of the gradient of f at p, and then cosine of theta, where theta is the angle between, right? So let's analyze this a little bit. So if we have cosine theta, we know that cosine theta has to stay between -1 and 1, just as sine does and stuff like that, right? So anyways, now if we want to find this whole thing, we can multiply everything by the magnitude of the gradient, okay? And when we get that, we get a negative magnitude of the gradient is less than or equal to the magnitude of the gradient times cosine theta is less than or equal to the magnitude of the positive magnitude of that gradient, right? So this would be when theta is equal to 180 degrees, right, or pi, right? Because that's when cosine is a -1. And the right side over here, the far end, that would be when theta is equal to 0, or 2 pi, or yeah, just 0, right? So just 0, okay? So if we look at this, this is basically, so what we're seeing is that something that's important to note is that the gradient of f, so gradient of f at a point p, this is it's constant, but the direction of our unit vector u can change or move around, right? Can change. We get to pick that, or it's given by the problem, right? But that can just, it's flexible, right? It can change or move direction. So we see that that's the only thing that can change the angle, right? So the direction of u in relation to our gradient determines like how big, or how, yeah, it basically determines the cosine of our angle. So the direction of u in relation to our gradient determines the angle theta, which also determines our cosine of theta, which determines our directional derivative. I'll just put dd for directional derivative, okay? And I'll write our conclusions on the next slide. So what that means is that, I'll write that up again, so negative gradient of f is less than or equal to the gradient of f at p times cosine of the angle between the gradient and u, and then is less than or equal to the positive gradient, or magnitude of the gradient of f. Okay, so we have this, and so we can say that when theta equals 0, then we're at a maximum, right? And cosine is equal to, this is like cosine of 0, right? That would just be a 1, right? Okay, so when we have that, cosine of 0 equals 1, so then we see that we get a maximum of our directional derivative. So this is a maximum. It's the most positive that it can get, right? So anyway, so the directional derivative is a maximum, and what that means is when the theta equals 0, that means that the angle between is 0, so there's no angle of like separation, like there's no difference in the angle. So that means that u is pointing or points in the direction, in the gradient f of p direction. Okay, it's pointing exactly in the same direction. Okay, so that's when we get a maximum. Another case is when we have theta equaling 180 degrees or pi, right? Then we get oppositely that we have this cosine theta, so that would be cosine pi. That gives us our -1, right? So that equals -1, okay? So then we see that our directional derivative is a minimum. That's the most negative it can get, minimum, okay? And when we see that, so theta being pi, or 180, a full 180 degrees, that means that u, the direction vector u, or the unit vector u, points in the complete opposite direction, in the opposite direction to our gradient at that point, okay? All right, and then the last case that I want to, this last like special case, I guess, that I want to address is when theta is equal to pi over 2, or 90 degrees, okay? Then we have that cosine pi over 2 is equal to 0, right? So then we have that the directional derivative is equal to 0, meaning that when we take the dot product between the gradient of f of p dotted with u, that's going to equal 0, right? So then we see that u is orthogonal or perpendicular, orthogonal to our gradient vector, okay? So that's basically it. I'll just say the conclusions one more time in more of like a physical sense, or a physical application, okay? So we have if u arrow is a unit vector making an angle, we'll call it theta, because that's what we've been calling it so far, with our gradient f at p, then we have that our directional derivative, so d sub u f at p, is equal to the magnitude of that directional derivative times cosine of that angle between, okay? So what we can say is that the gradient f of p points in the direction of the maximum increase of maximum or greatest increase, maximum increase or rate of increase, I guess that's more technically correct. So maximum rate of increase of f at p. And we know this because when our unit vector u, so this guy, when it's pointing in the same direction as our gradient vector, then we get that the angle of separation is 0, right? So then we get that cosine 0 is equal to 1, and our directional derivative is the maximum that it can be. It's the greatest that it can be. So that means that when u points in the direction of the gradient, then that's pointing in the direction of maximum rate of increase. Therefore, our gradient must always point in the direction of maximum rate of increase of f at that point p. Okay? And then conversely, we have that negative gradient of fp points in the direction of the maximum, and this time it'll be opposite. So maximum rate of, not increase but decrease of f of our function at that point p. Okay? And then one other thing to note is that f, the gradient f sub p, is normal, aka perpendicular. So normal, perpendicular to the level curve or surface of f at p. Okay, and what that means is basically when we have some kind of like, here's our curve, okay, and then we're at point p. Let's say this is point p, okay, and then we're moving this way, or it's moving this way along the curve, like the point is going this way, not the other direction. And then for the maximum rate of increase, we would have something like this, right? So this would be our gradient f of p, because that's where the curve is pointing, basically. And then maximum rate of decrease would be pointing this way, so negative gradient f of p. But anyway, so here we see that there's a right angle, so it's normal to the curve, okay? And then another thing to note, building off of that last thing, is that because our gradient f of p is normal to the curve, normal to the level curve or surface, because that is true, what we can do is kind of make it like, as far as like the equations of plane go and stuff, we can kind of consider this like the normal vector, okay, because it is a normal to the level curve or surface. So if we treat this like the normal vector, when we're dealing with planes and stuff, and tangent planes and whatnot, we can say that instead of n times x minus a, and then y minus b, and z minus c is equal to 0, we can replace that with our gradient, right? So now we have, and I'll just put an fp dotted with x minus a, y minus b, and then z minus c. And this, when you expand that out, what we'll get is actually something like f sub x at ABC, that's our point in question, f sub y evaluated at ABC, and then f sub z evaluated at ABC. We're going to dot that with the other things, which is kind of long, so I might not be able to fit that in, or maybe I will. There we go, equals 0. Okay, so what we would finally get for, and here I'm just trying to get to the equation of a tangent plane, so you could see how we could apply that. So f sub x at ABC times, when we do the dot product, we get that multiplied times the first component here. So these are the first two components, and then we're going to add that to the product of the next two components, ABC, and that'll be times y minus b, right? And then the last components are f sub z ABC, and then times z minus c. And this all equals 0, okay? So this is an equation, I don't know what happened to that n there, equation, there we go, of the tangent plane at ABC. Okay, so that's basically it. That is all for this video on the gradient and the directional derivatives. And I'm sorry it was so long, but there's a lot of material to cover, so I hope that really helped, and good luck on your homework.